Hello everyone, my name is Alan Rhodes and I'm a research scientist at Berkeley Lab in the Earth and Environmental Sciences area. Today I'm going to present on recent work that was funded by the Department of Energy through the Hyperfacets and Cascade projects. This work was largely enabled by Dahi Stone and Michael Weiner, who are both co-authors, and the International Detection and Attribution Group, or IDAG, associated with the IPCC, as well as Berkeley Lab's NERSC supercomputing facility. This work was published open access in Weather and Climate Extremes in May of this year, so feel free to check out our DOI. And the overarching goal of this study was to assess how coastal western US landfalling atmospheric rivers might change along several stabilized warming scenarios. This is important because atmospheric rivers are critical drought busters to the region, yet they can also cause major flooding, as shown by the 1862 and 2019 flood event examples on the bottom left. These characteristic changes in ARs with warming were then decomposed and translated into water management relevant information by building off of important work out of the Scripps Institute of Oceanography using the new AR category scale and their connection to historical economic flood damages. Also, notably, ARs stress test the capabilities of our cutting-edge climate models, as shown in the animation in the bottom right, highlighting a 3-kilometer resolution global storm resolving version of the Department of Energy E3SM model, codenamed SCREAM. As mentioned in the previous slide, one of the major goals of our study was to translate future projections of AR conditions into management relevant outcomes. To do so, we leveraged the Center for Western Weather and Water Extremes, or CW3E, AR category scale. This category scale decomposes flavors of ARs into those that are mostly or primarily beneficial to water resources, or ARs category 1 through 2, to those that are mostly or primarily hazardous to water resources, or categories 4 through 5. This AR category scale relates in AR's maximum intensity, measured through integrated vapor transport, and correlates with maximum precipitation intensity, as shown on the y-axis of the lower left-hand plot, to its landfall duration, which usually lasts between less than a day to 3 days and correlates well with storm total precipitation, as shown on the x-axis on the lower left-hand plot. These AR categories enable the decomposition of beneficial versus hazardous AR events and led to a seminal study by Tom Corringham and others showing that 84% of all flood insurance losses in the western US were associated with ARs, roughly $51 billion in damages over a 40-year period, and that a mere 13 of those AR events accounted for over half of the total damages, many of which were AR category 4 or 5, as shown on this figure on the far right. So since these AR category 4 or 5 events are so much more destructive, a critical question is how climate change may intensify such events and alter their frequency of occurrence. Therefore, to assess how climate change has already and may continue to alter AR characteristics, we leverage 2 IDAG-related simulations that utilize the Community Earth System model run at a global resolution of 25 kilometers. The use of a high-resolution global climate model simulation is important, as outlined in a Nature Review paper by Ashley Payne and others showing that thermodynamic adjustments associated with climate change are likely to enhance AR conditions through processes such as the Clausius-Clapeyron adjustment, whereas the dynamical adjustments associated with climate change through processes such as storm track alterations, tropical widening, and others might lead to reductions in AR conditions, particularly at local scales along the coastal western US. Further, many studies have assessed the high emission scenario trajectory of AR conditions, which peak at around 4 to 5 degrees C of warming by end of century, and fewer have assessed the warming levels in between that, which might now be more likely, notably a 1.5 degree Celsius future to a 3 degree Celsius future, as more climate policy is passed. So the first set of simulations that we leverage for this study are called the Climate of the 20th Century plus Detection and Attribution experiments. In these experiments, anthropogenic radiative forcings are set to pre-industrial values, or around year 1855, and sea surface temperatures are cooled by a space and time varying estimate of the warming attributable to anthropogenic emissions, as discussed in more detail in the study on the lower right hand called Stone and Paul 2021. The pre-industrial adjusted simulation is called NatHist and represents the world that might have been. The present day simulation is called AllHist and represents the world that is. And then the 3 stabilized warming scenarios are called the half a degree additional warming prognosis and project impacts, or HAPPY experiments. These experiments simulate a similar historical decade, roughly 2006 to 2015, but under conditions a century in the future, so around 2106 to 2115, using the representative concentration pathway, RCP 2.6, and or RCP 4.5. RCP 2.6 is used to estimate the happy 1.5 scenario, or plus 1.5 degrees Celsius since pre-industrial. And RCP 2.6 and 4.5 are used to estimate the 2 degrees Celsius scenario, or happy 2.0, or the unhappy scenario, the 3 degrees Celsius scenario. I'll briefly mention here that the details of the simulations can be found in Wayner et al. 2014, such as model specifics on the dynamics and physics time step, dynamical core used, and the subgrid scale physics suite. I'll also mention that these simulations were conducted under the Atmosphere Model Intercomparison Project, or AMIP protocols, meaning that the atmosphere and land models are coupled and freely interact, and the sea surface temperatures and sea ice data sets are prescribed at monthly intervals. The last noteworthy point is that all 5 experiments had multiple ensemble members, up to 6, all of which at least simulated overlapping 10-year periods of 2006 to 2015, or the future period of 2106 to 2115. So there's upwards of 60 years of data available. I'll also briefly mention how we track the ARs using tempest extremes, or specifically the spline ARs and stitch blob algorithms, the details of which are highlighted in 3 papers mentioned below. First, as shown by the visual in the upper left-hand corner, integrated vapor transport is computed across all levels of the atmosphere. Next, the integrated vapor transport is filtered using tempest extremes for only AR conditions. After, we track the AR from origin to terminus in the coastal western US and create a composite of the tempest extremes masks and find the weighted center of mass of those masks to identify the AR path over the entire North Pacific through landfall. We can then accumulate all of those AR paths for a given season or year, as shown in the bottom right. Last, our algorithm computes the components needed to compute spatially complete AR categories, namely max IVT and AR duration at each grid cell, as shown on the right for an extreme category 5 AR event. The first question we aim to answer in our study is how the distribution of all ARs tracked over all the 10-year periods and ensemble members across those stabilized warming scenarios might change. To show this, we plot every AR from each of the experiments on individualized AR category tables organized from the NatHist, or pre-industrial conditions, on the far left to unhappy, or 3 degrees of warming, on the far right. Each dot on the AR category table represents an individual AR event tracked. In summary, we found that the lifetime size and the life cycle duration of an AR increases by 15% and 6 hours per degree Celsius, respectively. Further, for every degree C of warming, 3 more atmospheric rivers on average occurred per year. Additionally, the average AR category of these landfalling ARs increased from 1.8 in the pre-industrial runs, or NatHist, to 2.4 at 3 degrees of warming. Next, we aim to assess how AR category frequency shifted with each stabilized warming scenario. So the plots shown here are the average number of AR landfalls per year for each warming level. Importantly, we find a subtle but notable uptick in the number of AR category 4 and 5 events with warming, whereby in the NatHist and all HIST experiments, these events occur 2% of the time, whereas in the unhappy experiment, these events occur 8% of the time. Further, AR category 1 and 2 events, or primarily or mostly beneficial to water resource management, decrease from 91% of the time to 78% of the time with 3 degrees of warming. We then assess how AR characteristics might shift in seasonality and intensity with warming. Akin to the last slide, we show stacked bar charts indicating the average AR category for each month of the water year, and ordered the plots from NatHist on the left through unhappy on the right. We highlight that at pre-industrial conditions, a more distinguished peak in AR activity occurred in January and February, whereas at present day warming levels through 3 degrees of warming, the November through February months are more evenly distributed in terms of AR frequency. However, the AR cat reached, particularly categories 3 through 5, become more regular with every degree Celsius of warming. With the help of my colleague, Mark Risser, we then assessed how the annual frequency of AR categories shifts in space with warming scenario using a statistical framework, namely a Poisson distribution combined with a spatial autocorrelation adjustment called a hybrid version of the conditionally autoregressive prior distribution, or CAR, to estimate return frequency probabilities. We lumped AR category 1 through 2 ARs per year with one another AR category 3 ARs and then AR category 4 and 5 ARs together, as shown in the top row, middle row, and bottom row respectively, and then each warming level is a different column. Using the simulations in this statistical framework, we found that there's a clear and systematic increase in the number of landfalling ARs in the Pacific Northwest with warming. For example, the probability of at least one category 3 and or 4-5 AR making landfall anywhere along the coast of Oregon and Washington is doubled from pre-industrial to 3 degrees of warming. And a 1 in 100 year event becomes approximately a 1 in 25 year event. Notably, California did show higher amounts of spatial noise relative to the signal associated with the warming, indicating that more ensemble members might be needed to constrain return frequencies, particularly those category 4 and 5 ARs. Our last analysis of the paper, and essentially the punchline, is that we estimated how shifts in AR categories associated with warming shape the potential economic flood damages per year in the coastal western US. The economic flood damages were gleaned from the hard work of Tom Corringham and the CW3E team at Scripps, who compiled statistics on 40 years of flood insurance losses and associated them with each AR category. To translate flood damages from the model world using these historical real-world flood damage estimates, we first fit a statistical distribution, namely a skew-T distribution, to the observed damages for each AR category, which spanned between $10,000 and $5 billion per event. We then, using the all-hist as a baseline, calculate the percent change in the annual AR counts by category from the simulations. We then apply these percent changes to the historical annual AR counts and resample the cost distributions with these modified counts using a Monte Carlo approach with 1,000 replicates. Using this approach, we found that average flood damages per year is estimated to be about $1 billion per year in the all-hist experiments, which is comparable to the estimates providing in Corringham's study. Once we got appropriate distributions to sample from, we applied these distributions and resampled with each warming scenario. We found that for every degree of warming, on average flood damages increased by about $1 billion per year, largely through that subtle but important increase in frequency of category 4 and 5 ARs mentioned earlier. Notably, we do not account for spatial dependencies of AR landfall, such as if they make landfall over urban areas or at-risk infrastructure, or potential damage mitigation through societal innovation in water infrastructure and management, or potential damage amplifiers such as compound or sequential extremes. I will now summarize our findings, but first I'd just like to note that it is important to be reminded that there is still ample time to limit warming to below 3 degrees Celsius of warming since pre-industrial times. However, there is potentially a lot at stake if we don't. Namely, the number, frequency, and range of months that more hazardous ARs can occur will increase across coastal western US states with warming. Notably, an increase of 3 degrees Celsius of warming will lead to a subtle but important uptick in the number of category 4 and 5 ARs, from approximately 2% of the time to 8% of the time. This uptick in category 4 and 5 ARs results in a tripling in annual average AR flood damages from approximately $1 billion per year to $3 billion per year. I'll also note that there are plenty of uncertainties or limitations to our study, such as the fact that we only use a single model, the community air system model, which has known issues in producing too many ARs, hence why we bias corrected our economic flood damage estimates towards Corringham's estimates using the all-hist simulation. We also note that 25-kilometer resolution is cutting edge for global climate modeling. However, topographic complexity, particularly in the Cascades, might be underrepresented, and therefore interactions with orographic precipitation might be underrepresented. We also only use a single AR detection algorithm, which has been shown in recent studies to play an important role in future climate change analyses of ARs, namely if an AR algorithm has absolute or relative thresholds. We also found a low signal-to-noise ratio and spatial return frequencies of ARs over Southern California in particular, specifically with category 4 and 5 AR events, indicating the need for more than 60 simulated years to get a stronger signal with warming and shifting AR conditions. Last, I'll just note that we may undersample climate modes of variability, as the 2006 to 2015 period does not have very many moderate to strong El Nino events sampled. But with that, I just thank you for listening, and I'd be happy to take any questions.